exam, right? And it might be uniform, and it might not. So your first pass, you see a circuit of motion problem. Is it uniform or not? Right? Is it speeding up, slowing down, or is? And in fact, you can have a situation where it's non-uniform circuit of motion, but momentarily the object isn't speeding up or slowing down, right? And then you know the acceleration vector at that moment in time. You're pointing straight to the middle of the circle. But at other moments in time, it won't. And so knowing how to think through that kind of stuff. So that's important. Might show up. All right. What else? Well, lots of stuff, right? We learned a whole bunch of physical laws. In particular, we learned Newton's second law, Newton's third law, Newton's second law. If I were you, when I'm going to use Newton's, well, here, let's do it this way. When I'm going to use Newton's second law, I would write N2L right there so the grader knows what you're doing. That way, if you screw up, you leave something out, and the grader's wondering, does the student understand, what equation is this? They'll say, okay, this is the right equation, you made a mistake, you just left off the force of friction when or whatever it was. So after that, X component, maybe you'll do it. I usually label X, like here's for the X direction, just so it's clear. A lot of students, you're juggling lots of different concepts with just a few symbols. So use subscripts. I usually go overboard, as you know, but do whatever it takes so that you're clear on what direction you're talking about. And so yeah, what is it, F equals MA? Right? And it better be the right M. There's three masses in the problem. You have a block that's hanging over here. There's another block over here that the gorilla's walking off with, or whatever it is. Make sure you label this with the right M. And make sure that this acceleration corresponds to the force. This is the force on the object that has this acceleration. Right? And if it's X component, it better be X component over here. If it's Y component, it better be Y component. Right? Anyway, yeah, Newton's second law. Now, do you use free body diagrams in conjunction with Newton's second law or Newton's third law? Second law, that is correct. So I always draw, and in fact, you'll be asked probably somewhere on these based on my old exams, just looking at my record. I tend to ask you questions about some part just to make sure you can draw a free body diagram. So if you've got a problem with gravity, okay. I don't care if you label it mg or if you label it f sub g, whatever. As long as it's clear that gravity. Label your forces. Also, some people can draw the arrows in versus out. That's fine. Just make sure the direction of the arrow is the direction of the force. So if you want to use, if you're drawing gravity, it better be straight down. I don't care if it's down towards the dot or down away from the dot, but you better not have it away from the dot point, not going to lose force, right? And again, if there's multiple masses in the problem, label your mass here, right? Okay, gravity has to label. Everyone has the same G, but different masses, right? And whatever, you know the rest of it. You can have a force due to gravity. You have a normal, excuse me, not gravity. Friction. You can have a force due to normal force. Symbol like N, like F sub N to remind you that the force. Whatever you want to do is fine. Maybe there's tension. I usually use 15 not F sub T, so I guess I'm not consistent. But as long as it's clear to the grader what you mean. Ropes only pull. Yeah, you know. Okay, super. Newton's third law. If you use Newton's third law to figure something out, just go ahead and label it. And what is Newton's third law? It just says that the force on A on B is equal to minus the force of B on A, right? And there's a lot of cases where you'll use this implicitly. We use this all the time, sort of implicitly. And that's okay, as long as the grader can tell what you're doing. But go ahead, if you find yourself using this law to figure something out and it's relevant, go ahead and label it. Great. Friction and normal forces, so contact forces. If you have any force that's perpendicular to a surface, right, a component of the force between the surface and the chalk, if I'm pushing the chalk that way a little bit, it's got a normal component and it's got a frictional component. So it's actually pointing that way, right, if I push the chalk that direction, right? So the result is that you'll have normal force, know how to use that, right? But also know how to use frictional forces. We have generally talked about two kinds, kinetic and static. This guy, if I'm pushing on the chalk and the chalk's not moving relative to the table, is it kinetic or static friction? Static, that's right. And which one's got the inequality? Static or kinetic friction? Static friction has the inequality, and you know why? Because if it's sitting there and it's not moving, stop moving. All right, then see that? The control I got. This thing's not moving. And why? What does that mean about the friction? The force of friction? It means that it's zero. Because there's no other horizontal force acting on it, so that means the balance of forces, right? Static friction balances out the forces to make them zero, so the thing's not moving. It must itself be zero. Whereas kinetic friction, if you have kinetic friction, it's going to, what's the direction of kinetic friction? It's going to oppose the velocity of the object. So if this guy's sliding this way, you know the kinetic friction's going that way. I don't care if it's on an incline, right? If this guy's sliding up the incline, which way is the force of kinetic friction? Up the incline or down the incline? Down the incline. So now the force of kinetic friction is helping gravity trying to turn this guy around, right? So it opposes the motion. It doesn't balance the forces. Whereas static friction always, if it's sitting up on, there we go. Static friction is always going to oppose the force of friction in a case like this because there's a balance, force of gravity. The component of gravity is along the incline down the slope, so that means static friction must be up the slope. If it's not moving, you know that must be true. Now, if there's also a spring on this thing, or there's somebody pushing on it, then okay, you have to consider the net force excluding the force of friction to see which way force of friction is pointing. Right? But if it's just gravity, we know which way it's pointing. Okay, great. So yeah, inequality, that's right. Force of friction, kinetic, that just equals mu sub k times the normal force. This is not a vector equation. These are magnitudes. This thing has no units, right? And if you want to figure out what this is, you have to sometimes solve Newton's second law separately to figure out what the normal force is. And it can depend on gravity and a bunch of other stuff. Okay, great. All right, before you guys nod off. Moving. So I'm finally going to get to this demo today. That's good. We'll do a little ballistic pendulum, which is good because that's when you really need to know for the second term. Is how you handle cases, how to know when you're using conservation of energy and when to use conservation of momentum. Now, for next week's exam, you're not going to have to worry about conservation of momentum. You're allowed to use it. You can use any physics law you want. If you want to use relativity and some general relativities, right on. Keep us up all night in your exam. You'll still get good credit for that if you do it right. But so you're allowed to use what you want. But I'm not going to have any problems that require that you use that to solve it. I'm not going to have any problems that are designed so you need to use conservation of momentum because we only covered it this week and exams this week. So I want to make sure you've got enough time to think about whatever shows up on the exam. But you could see all kinds of conservation of energy next week because we've been covering that for a while. Right? But okay, so force of friction, static, what is that? Oh yeah, I wrote an equal sign, but really it's an inequality. Which way does inequality go? So is it less than or equal to, or is it greater than or equal to? It's less than. That's right. There's a maximal amount of friction you can get, a force of friction you can get. It's bounded from above by how much normal force you've got times some coefficient that depends on the material at hand. Okay, good. And you're going to have it written down, I know, but it's good to understand it because as you've seen with me on the board, I'm holding my notes, right? Right? I can make lots of mistakes on the board, which is kind of like being in a test situation, right? Because you're in the same sense that you're being scrutinized or you're under time constraint. People are watching in a sense, right? So the thing is, you want to be comfortable with it as well as having it written down. Having it written down on your sheet is great, but you also want to have a feeling for why it's true, and you'll be able to avert errors, right? Especially, you may even have a typo on your formula sheet. But you can recover from that if you understand the stuff on it. Okay, great. So yeah, Hooke's law for springs, the force in the x direction, let's say, is negative, let me make sure I say this right. Oh yeah, we want to use k, right, for our spring constant, times delta x, right? Where delta x is the displacement from the equilibrium position. Delta x equals 0 is a special point. It's not arbitrary. I apologize to those of you who are looking past this thing at the board. Anyway, so these are all equations you've seen a million times, but just to jog your memory. Yeah, so okay, let's do a little bit more of this, and then I'll see if there's any last minute questions, and we'll get on to some new stuff. Yeah, ropes only pull, and we usually use capital T for tension in the rope. And pulleys, yeah, pulleys do a couple different things, right? If you have an ideal pulley, it means it's massless, frictionless. If you have an ideal pulley and an ideal rope, then that means the tension everywhere in that rope is the same. That's a wonderful simplifying fact for you, right? The only cases where you won't see ideal pulleys in this class, like later in this course, we're going to have pulleys that are not ideal, that have mass. And that'll be important because it turns out that it takes energy to start spinning up a wheel that's got mass. But if you have if you have an ideal, a massless pulley, that means the tension everywhere is the same in a given rope. And what else does it mean? So we've had problems where you pull on a rope and then there's a pulley and something moves, but as a result, right? If you saw with me in that bosun's chair, right? You had 3 pulleys down here and there were 3 pulleys up here, right? And so tension's the same everywhere. These are all we assumed they were all ideal pulleys, right? And this goes up to the ceiling. If I call it the ceiling. Anyway, here we go, right? But in this case, right? How much rope? Like if the student pulled this thing over by, let's say, by 1 meter, how high would I go up in the air? How high would this chair go up in the air if I pull that rope by 1 meter? What is it? Well, is it 7? Is it 6? The student's over here pulling on this rope. The rope moves over by 1 meter. How high do I go? Is it 7 or 6? 6. And the way you know that is you're counting. I apologize again for this one. You're counting the number of ropes that are coming down. You're saying how many of these things have to get shorter? This guy gets 1, 2, 3, 4, 5, 6. This guy doesn't need to get. It's not connected to me. If I were holding it with my hand now, for me to go up by, well, let's see, depends on how I measure. If I go up by, let's say I go up by a meter, then how much rope do I need to pull? Let's ask that question. Well, when I say how much rope do I need to pull past my hands, the answer is 7 meters. If I ask how much rope piles up on the ground, it's 6 meters. The reason there's that extra meter for me pulling on the rope when I go up is that I moved up by a meter, right? After all, the same amount of rope had to come off the top of that pulley, whether a student pulls it or I pull it, for me to go up by 1 meter. 6 meters of rope had to go past that pulley. That means on the ground, 6 meters of rope is piled up, right? Beyond what was there before. But in terms of past my hands, if I start down here and I go, my hand moved by, anyway, you get it. I'll say it 10 more times. Yeah. Repetition is the mother of learning, and I guess I'm the mother of repetition, I apologize. But there's some things that are worth repeating. The main thing is on the exam, you probably won't see this many pulleys, but you might. But just remember that when you're calculating the work, what's work? Force times distance, right? This is the case where the force is only in the x direction and the displacement was only in the x direction. It's also a case where the force was constant because I didn't write it as an integral. You're not going to do any integrals on the exam. Well, that's a little bit of a lie. And people are shaking. Oh my gosh. By that I mean you can certainly use an integral to solve problems, but you won't have to. There's always going to be a way to do it without actually having to perform an integral. But you're always doing an integral. Whenever you write any stuff, this right here is the solution to an integral. It's just such an easy one you don't bother to think of it that way. That's all I mean by you need to do integrals on the exam. And you're of course allowed. You want to do some hyperbolic, whatever, do it, but you don't have to. So you got F in the x direction. Oh yeah, so constant force. So that's why I can just put F here. It's the same at every point in time along this, or every moment, every location along the displacement, right? And what else? Oh yeah, so it's pointing in the x direction. In general, right, we have to worry about things like the dot product, right? If we have, if the direction isn't necessarily the x direction, if the direction of motion isn't just in the x direction, or if the displacement of the object isn't parallel with the direction of the force, that's what I'm trying to say. Then you have to worry about the dot product, right? You have to worry about the fact that, like if I'm pulling my luggage, right, and I've got a strap, and the strap's up at some angle theta, and I'm walking along, right? Well, in that case, the displacement's going to be in that direction, but the force, right, is going to be in that direction. So, in that case, I need a dot product. In particular, I need to take a dot product of that angle theta. Right? That's the theta that I'm putting in right here. I'd say, oh yeah, it's the length of the force vector times how far you move times cosine of that angle theta, right? You all know this. Okay. Good. And in terms of science, it's really important to understand science for work. When you're talking about work, I can talk about the work that's being performed by one particular force, like gravity. Be positive or negative. Is the work on the chalk due to gravity positive or negative when I do that? Work due to gravity, positive or negative on the chalk? Negative, because the force is that way, displacement was that way. If I say what's the net force on the chalk, it starts off going at 100th of a meter per second, or 20th of a meter per second, and it ends up at the same speed. What was the net work done on the chalk? What's the net work on the chalk? 0. By the work energy theorem, in fact, at the end, it started off at some speed and ended up at the same speed. The speed didn't change. So the kinetic energy didn't change. Well, net work must have been 0, right? Doesn't mean the work on gravity was 0. It means the net work, the work done by all the forces on the chalk. What are all the forces on the chalk? There's gravity, there's wind resistance, well, not much, we can say that's 0. And force from my hand on the chalk. So did I do positive or negative work on the chalk? Positive work. In fact, it was equal and opposite to what gravity did. That's why the net work was 0, right? Okay, be comfortable with work, as I know you are. All right. Oh yes, potential energy, so you've got potential energy due to gravity. We've already solved that integral many times. It's always the same with MdH. And by h here, I mean really delta h. I mean for the change in potential energy. Now, of course, we can define a 0 point somewhere, and then say h has some absolute meaning, some height 5 meters above the 0 point. Well, then you put in 5 meters for h. That's I guess how I mean it here. I didn't put deltas. That's what that must mean. And I made some decision about where the 0 point was for gravity. I'm allowed to do that for gravity. I can set 0 point anywhere I want. But for a spring, I don't have such a luxury. The potential energy for a spring is 1/2 k delta x squared. Is that right? That's right. It's always positive. Well, it can be negative. It's never negative. Never negative. This can be positive or negative. If you actually went from here to there, you lost potential energy due to gravity. But for a spring, you always have positive potential energy, and it goes to 0 when delta x is 0, and that's a special point. That's the equilibrium point of the spring, right? That's when the spring is not stretched or compressed. Okay, delta x equals 0. Okay, great. Conservation of energy. Good to know. And remember, when you have conservation of energy, you can still use it in some cases even if the system isn't closed. If the system is closed, it means there's no external forces acting on it, then the final energy equals the initial energy. But if you have some external force acting on a system, you can include that as a work term. You can say, oh, energy final minus energy initial equals some work due to external forces, right? But if you put external forces in here, if you put gravity in for your external force, because the Earth and the Earth's gravity is outside of your system, right? That's reasonable. Usually you have a system that's like this chalk, or the chalk and me, or something like that. And gravity can be thought of as an external force due to some other agent outside of my system, through the Earth, right? Well, if you put it as a work term, you better not put in potential energy due to gravity on these two things. And what I like to do, as you've seen, is I put potential energy due to gravity in here, I put potential energy due to springs in here, I put all that stuff in here, and I don't have any external work due to gravity or springs. But if there's kinetic friction in the problem, that can show up over here. How about kinetic friction? Is that right? Kinetic friction, that can show up here. How about static friction? Does static friction ever show up as a work? Static friction will never show up as a work term, provided that the two objects that are exerting, so suppose this thing's exerting a frictional force, on this guy's a static frictional force, as long as my coordinate system is holding still with respect to these objects, which is almost always the case in this class, you're not going to get a work from that. You get 0 work from that. So you're only going to possibly have kinetic friction over here at the external work, right? But you have other things too. You got somebody push on it, right? Or solid or a spring or something else that's not part of your system. It isn't just friction that shows up in the external work term. It depends on how you set up your system. It's up to you what you want to call your system when you solve the problem. Okay, yeah, you know the Pythagorean theorem. You know the rate to circumference of a circle. You know how to break things up in components. You're probably going to see a ramp on the exam. I mean, I don't know, but you might very well see one, or something. Maybe a circle, and there's at some point at the top, the ramp, the local angle of the ramp on some circular path, or I don't know whatever it's going to be. Well, just make sure you know how to break up the force. Let's take force of gravity, for example. Maybe if I choose this to be my x-axis and this my y-axis, I'm going to definitely show that to the graders. They know what I'm talking about. But I'm also, once I make a choice of axes, when I break up other vectors into their components, these are the axes, these are the directions of the components, right? So what I've seen students do a lot is they'll break up, they're so used to doing this, breaking into components, that even if they choose the vertical and horizontal directions to be their x and y axes, or y and x axes in that case, they'll still break up the vertical gravity force vector into components. But you don't have to do that, right? You've chosen axes that are lined up with gravity. It's already lined up and break it up. But if you have to break it up like this, what do? You have one that's parallel with x, one that's parallel with y, right angle, F, G, you got it. And this thing is going to be, oh yeah, where's the angle go? So is the angle up the top or the bottom? The angle theta in this picture, if it corresponds to that. This guy's perpendicular to that guy. This guy's perpendicular to, what did I do? Oh, this guy's perpendicular to, excuse me, oh man, let me say that again. This is parallel with him, he's parallel with him. And that means that, yes, right, this guy is perpendicular to him, and he's perpendicular to him. So that means that the bottom is going to be theta. And that was probably more confusing than it had to be, but if I'm smart and I make a really small angle here and a bigger angle there, then just by drawing my picture accurately, this is going to be more steep right here because this is a very horizontal line, and similarly here, it'll be more horizontal angle. Like, just make sure that this winds up being the smaller angle if I draw the picture carefully. And that's how I don't have to get confused, right? Thinking what I just did a minute ago. It's a lot easier just to draw careful pictures and get it right. So that's what it's going to be. And this is where the right angle is going to be on the opposite side. Okay, you know how to do this. Great. Know how to deal with dot products. Know how to deal with, power. Power might show up. What is power? It's the dW dt, where W is work, right? Power has units of joules per second. Joule is energy per time. So that's kilogram meter squared per seconds to the third, right? Lots of stuff floating around. So I usually think of power as watts. We'll see what watt. The thing that's unfortunate is that watts, W for watts looks like work, and meters looks like mass, and M is M for both. So just keep your symbols and your units separate. Be really careful how you write things down so you don't get it all confused. Okay, great. So that's what's going to be covered pretty much. There's things I didn't say explicitly right now that are going to show up most likely, but go through your chapters, look at the chapter things, the summaries at the end of chapters 1 through 7. Are there any last minute questions about this before I launch into some new stuff? Yeah. Yes. That's a good question. Discussion sessions happen all the scheduled times. Office hours are as usual. My current plan is to have a lecture next week on Thursday. But I think what I'll probably do is have some Q&A, right? Let you guys ask some questions. Because by then you might say, you've tried my exams and there's something that's really confusing, or I don't know, something. So what'll probably happen on Thursday is I'll open it up for questions at the beginning. If anybody has any questions, I'll cover some new stuff. If people have lots of questions, then that's probably what we'll do. So let's plan. Yeah. So plan on. If not, I'll send an email. If it turns out if I get feedback and no one's going to be able to, I might send an email saying that we won't have a lecture that day. But I think we will. Okay. Yeah. All right. So what have we learned on Tuesday? What we learned, and you need to know this. So I know that there's a lot of stuff to think about for next week, but there's stuff that's going to come up. The next term comes up fast. And learning new stuff actually makes you understand better the things you already learned. Physics is very much like that. So what did we learn? We learned about center mass, right? We learned about total mass. Just some of them. I'm going to write these things down. We learned that we learned a bunch of things we learned a bunch of ways of simplifying the way we think about systems of particles. And there's more than one object around. Now the first one, conservation of energy, right, which where we're talking about a bunch of objects and say, hey, energy is conserved, which can show up in next week's midterm. That is the first thing we learned, I think, where we saw a real benefit to thinking about Newton's laws and extensions of it in the context of a many-body system. But what else did we learn? Well, we learned that we can think of Newton's second law for a system in a couple different ways, right? We can think of it in terms of individual parts, but we can also just write down this, right? We can say, oh yeah, the net force in total, meaning acting on every object in our system. So the net means it's the vector sum on any given object, and then total is also a kind of a net in a way, but it means add up the net forces on all the objects and put them all together. This thing equals ma, right? But what this m is what? It's the total mass of every individual part. It's the chalk plus it's me and the chalk, that's the system. This is my mass plus the chalk's mass. And this acceleration is of what? What special point is this acceleration referring to? Center of mass of the system, right? Another thing we learned was that the momentum, right, of the total system, the capital P for that, it's a vector quantity, right? So well, we can think of this as the sum of the individual momenta, right? MV, right, for each of the different, and I'm using I here for each of the n different objects inside of my system. I can think of it that way, but I can also think of it as, again, the total mass of the system times the velocity of the center of mass, right? So this is, again, another kind of simplification. There's a third one we didn't get to last time that's very important. It's going to be very important over the next couple weeks, and that is the kinetic energy of the system. So what's the total kinetic energy for my system, right? What is that? Well, we can think of it as the sum of 1/2 mv squared of all the different m's and v's, right, of all the different parts. But we can also think of it another way, which is we can break it up into two pieces. We can say there's a kinetic energy of the center of mass, plus there's the kinetic energy internal. So this isn't quite as simple as the other equations I've had where I just have one new term that's the simple thing. Now I get one simple thing. What is this? This guy is just 1/2 total mass, you guessed it, times velocity of the center of mass squared. It's exactly what you'd expect. Is that right, everybody? This is the center of mass kinetic energy. But there's more, but there can be more there. And this isn't always all there is. If this guy right here is a rigid object, it's a piece of chalk that's moving, let's say it's moving to the right or your left, it has some kinetic energy, 1/2 mv squared. This is a collection of particles, right? There's stuff over here, but we tend to think of it as one object because it's rigid, and because we've been sort of keeping it simple so far in this class, right? But suppose it were rotating. Suppose this guy were rotating in the air as it went to the side. Now, even if I move along the center of mass and watch it, so before I did that, it wasn't moving anymore. So I say, oh, it's not moving in my reference frame. If I move with the center of mass and watch it, it doesn't get moving to me. So there's no kinetic energy. But it's rotating, even if I walk along the center of mass. The center of mass is right in the middle, right? So I'm staring right in the center of the chalk. What I see is this rotating thing. Now you guys see it translating and rotating.